is going to shift in either direction. So what are those conditions that you can increase or decrease pressure, temperature, or concentration? So if you, so I'm just going to explain this very quickly. You already know this. Increased pressure. What happens that the equilibrium is going to shift to the less gas mole side, right? That's the one that's going to be favored. If you increase the temperature, then the equilibrium is going to shift to the endothermic reaction. It's going to favor the endothermic reaction. So one of the reactions is going to be favored. Vice versa, if you increase concentration, then your equilibrium is going to try and do the opposite, which is equilibrium would favor that reaction that decreases concentration. So it's going to favor the reaction that decreases concentration, and then the opposite is also. And the opposite is also true. So, and vice versa. Right? You know this all right?
Yes.
I said now, so remember, when you have an equilibrium reaction, if it goes in the backward direction, I'm gonna take the same reaction that we quoted above. Now, standard conditions are that under standard conditions, the concentration of the ions is going to be 1 mole per dm cube. So if I do anything, the equilibrium would get shifted. It would either favor the backward reaction. So remember, in the backward reaction, more electrons are going to be produced. So if it favors the production of electrons, the potential would decrease. So the way equations are written in the data booklet, conventionally speaking, they're always written that in the backward direction, they lose electrons, right? So if the backward reaction is favored, or the one that produces electrons, is favored, then the new potential would be lesser. It's going to be lower because a lot more electrons are going to become more negative. So the potential, the non-standard potential, I'm not going to put an E naught on top. Potential decreases, or we can say that it becomes more negative. Vice versa, if the forward reaction is favored, and in the forward reaction, it's going to gain electrons. So that is what's going to happen in the forward direction. In the backward, it's going to produce electrons. So if it's going to gain electrons and that reaction is favored, then in that case, what will happen is that the potential would increase. And it would become more positive. Is that clear? So for example, if I do a reaction in which the concentration of iron ions is now 0.01 mole per dm cube. And the concentration of Fe 2 plus ions is 1.5 mole per dm cube. Where do you think would the equilibrium shift? Backwards or forwards?
Backward.
So it's going to shift in the backward direction. What would happen to the potential? I mean, the E naught is 0.7.
Potential will decrease.
So it's going to decrease. It's going to be, the new potential would now be without the naught on top. Maybe it's point. So I'm just going to take a hypothetical value that's going to be 0.56 volts, right? So just a hypothetical value, right? Is that clear?
Yes.
So anyways, you can do any of the above. You can change pressure, temperature, not really, because you don't know which one is endothermic, which one is exothermic. But if you had known, you could have sort of shifted it. Usually it's concentration or pressure that you can change, because the temperature, the endothermic, exothermic part is not usually written in with the equation. Is that clear?
Yes.
And most of the questions would be about increasing the feasibility of a reaction. A lot of them actually. So for example, I've got this Fe3 plus, I mean the same reaction. And let's talk about an actual reaction. It's one electron in equilibrium with Fe2 plus, right? And the E naught is 0.77 volts. Same one. And I've got another reaction. And remember, higher potential gains electrons, lower potential, it loses electrons. So I've got another reaction in which I have copper 2 plus 2 electrons in equilibrium with copper. And the E naught for this one is, according to the data booklet, it's 0.34 volts. So first you tell me, who's going to gain electrons, who's going to lose electrons? What's the overall reaction?
Fe2 plus is going to gain electrons. Yeah,
So
in the forward, and Cu it will be backward.
And you need to multiply this by 2 so that the electrons are balanced. Now, one second. So now that's what's happening. And we can write the overall reaction. It's copper reacting with so copper is reacting with 2Fe3 plus, and the products are copper 2 plus, and in the first one the products are 2Fe2 plus, and it's got a certain E naught cell, which is 0.42, 43, I think.
0.43.
So it's a feasible reaction, right? So the question now is, how can you make it more feasible? Or how can you increase the E naught cell? So you can increase the E naught cell by increasing this potential and decreasing this potential, right?
Yes.
So you want to make this higher, and you want to make this even lower. Basically, you want this to go in the forward direction even more. You want this to go in the backward direction even more. So what changes could you do to make it higher, to move?
First one, you can increase the concentration of Fe3 plus.
So you can increase Fe3 plus, or you could decrease, like assuming it's a cell, or you could decrease the concentration of Fe2 plus, right? Is that clear? And what about here?
Well, you have to increase the increase the concentration of copper.
I just remember one thing. Where's our rules? Here. I said, remember one thing, when you talk about concentration, the term concentration over here, it only applies, concentration is a term that's only used for either gases or solutions. Not for solids, because remember, what is concentration? Concentration is kind of the spacing of the particles, right? If the particles are like really far apart, that's less concentrated. If the particles are really close together, then that is concentrated, right? So you can only change the spacing in a solution. Like if there's a solution, then the particles, if you add fewer particles, the particles would be far apart, right? You add salt to it, or if you add more particles, then the particles would be more concentrated. They would be very close together. Is that clear?
Yes.
Or you can do that for gases. Like you can do the same thing for gases. There's a container. If because gases, they tend to occupy the whole volume, so the particles would be far apart or they could be close together. So you can compress a gas. You can change the concentration of a gas, but not for a solid, because in a solid the particles are all tightly packed. The same applies to liquids. Pure liquids, you can't change the concentration. And like if you can't change the concentration of water because the molecules are already right next to each other. You can't change the spacing. Is that clear?
Yes.
So remember, so solids, I'm just going to add this here. Solids have a constant concentration. So solids and pure liquids, so they have constant. So they've got constant concentration. So you can't really do much over here with copper. That's kind of fixed. But you can decrease the concentration of copper 2+, right? So over here you could decrease copper 2+ concentration. I said now one second. I said now the next thing is so remember this, you can sort of alter the concentration. You'll get questions about this. So make the higher potential higher and make the lower potential lower. Sometimes some of the equations will have gases, so you can kind of change the pressure as well. Is that clear? Raji, is this clear?
Yes, sir.
So then you would be asked to calculate the non-standard potential. Like one way is to just guess it, like it's going to be higher or lower. And the other way is you actually go and measure it. So you're going to get two types of questions. They just want to increase the potential or the potential difference of the E0 cell. Or they would ask you to calculate the non-standard. E0 cell. Not the E0, the non-standard E. And for that, they're going to use the Nernst equation. So there's an equation, but that equation only works with concentration. I mean, it won't work for pressure. I mean, it's got no pressure term, so only for concentration. So only for concentration. And remember, solids, the concentration would be taken as 1. Like it's going to be taken as a constant. So I've got, and what this is the equation. It's the new potential is going to be the old potential plus 0.059, which is a constant, divided by Z, which is the number of electrons, and log of the oxidized substance and its concentration over the reduced substance and its concentration. And its concentration. So remember, log is just, you know what log is? Are you familiar
Yes.
with? Z is so I just clarify a few things. Z is the number of electrons that are in the equation. Oxidized is the one, it's the species that is formed after oxidation. It's a species formed after reduction. So in the conventional way that equations are written, the species that is formed after oxidation, like if you look over here in the iron equation, which one out of the two is the species that is formed after oxidation? The left one or the right one?
The left one. No,
Left
the
one.
right one.
No, the left one, formed after oxidation. Like
Oh, then it's the
Fe2 plus
right
got
one.
oxidized, and it's a species that is formed after oxidation, right? So it's going to be this one. So it's the left one, basically, like in the conventional way that equations are written. So species formed after oxidation, that's basically the one that's on the left. And this is the one that's basically on the right, the one that is formed after reduction. So I'm going to take the same, let's take the tin 4 plus equation. So I've got tin 4 plus 2 electrons, and it's in equilibrium with tin 2 plus. The standard potential for this one is, we can just quickly open this. So the standard potential for the tin equation is, it's over here. The tin 4 plus tin 2 plus equation, that's 0.15 volts. So the E naught is 0.15 volts. So let's, so the E naught is 0.15 volts, right? But now I'm going to move towards non-standard conditions. So this one is, first thing is we're going to guess. So this is 1.2 mole per dm cube, right?
Yes.
And that one is 0.01 mole per dm cube. So what do you think? What should happen? Potential increase or decrease? Where would the equilibrium shift?
Equilibrium will shift towards SN4 plus.
And what
So
will
it
happen?
will
Higher or lower?
lower.
If it moves in the forward direction, right? So it's going to become
Oh, yes,
higher.
higher. Yes, higher.
I mean, I think I wrote somewhere. I mean, this is the important point. Basically, let me highlight this. So if it moves in the forward direction, if it gains electrons, it's going to become higher. The easier is that if it starts to lose electrons, and that reaction is favored that produces electrons, the potential would become more negative because obviously there's going to be more electrons. So in this case, it's going to be higher. So it's going to be greater than 0.15, right? Is that clear?
Yes.
So we're going to calculate now. The Nernst equation is given to us. So the new potential is basically the old potential, which is 0.15. So it's the old potential. So it's 0.15 plus 0.059. What is Z? It's the number of electrons, which in this case is what? How many electrons? That's going to be 2, right?
Yes.
And log of oxidized species. So what concentration should I put over here?
Oxidized,
Is it 1.2 or 0.01? Log of oxidized species over reduced species.
oxidized is 1.2
It's 1 point.
over
Okay, so it's 1
over
point.
0.01.
So it's basically 1.2 divided by the other one, which is 0.01, right? And can you do the calculation and do the math, and we'll get a value. Tell me that value.
Zero 0.211.
So we're getting
0.21. 0.21.
So we're getting 0.21 volts, which is true because, I mean, this is what we predicted. We predicted that's going to be higher than 0.15. So we are getting something that's higher than 0.15. And also remember that it's not going to be that big of a change. Like, I mean, the change is kind of really small. It's 0.15, this is 0.21. And you can see that the concentrations have really altered. I mean, this is 1.2 mole per dm cube, that's very less. Even if there's a big change, the change in potential is not going to be that huge or massive. So remember, the potential change would only be just very slight. Like if something is 0.15 volts, it will not become 1.5 volts. Like it's not going to be a 10 times change that will happen. Is that clear?
Yes.
So just a slight, it's going to be slightly higher or slightly lesser. That's about it. So not a massive change. Another way that questions that get asked about this is that you've got unfeasible reactions and you try to make them feasible. So for example, see, you understood how to calculate the potential, right?
Yes.
So you've got an unfeasible reaction and you try to convert it into a feasible reaction. So for example, let's take the same 10(2) plus equation. Sorry, 10(4) plus. And it's turning into 10(2) plus, and the E naught is what? It's 0.15 volts, right? And I've got another reaction. Let's pick another equation that is very similar to this, something close to 0.15. I think there's one copper equation, but that one is exactly 0.15. Something. So for some reason, we don't have anything close to 0.15. Let's take minus 0.04, this one, or minus point. So let's take this one. Where's the minus 0.04? Let's take this Fe3 plus. Just 1 second, let me copy this. So I've got Fe3 plus I think that's 3 electrons and turning into Fe, right?
Yeah.
And it's turning into Fe, and the E naught is minus 0.04 volts. So let's come back to this. Now, according to, and it was minus 0.04, I think. So according to, who's going to gain electrons? It's going to be the higher one, right? So let's I mean, that's supposed to gain electrons, right? But let's say I do this. I say that the first one loses electrons and the second one gains electrons. And we can multiply the first equation by 3, I think. So this
Yes, and the second by 2.
so this gets multiplied by 3 and the second by 2. So that multiplies by 2, that multiplies. And I can write, and then, I mean, this is, I mean, you're, is that clear? This is not going to happen, right? The way I've drawn the arrows, right? So my unfeasible reaction is that there is 3 SN2 plus, and they're reacting, that's my reactant, and the other reactant in the other one is 2 Fe3 plus. And the products that they are making are, so what are my products? The products that they are making are, in the first one, it's 3SN4 plus. And in the second one, it's 2 Fe, right? So this reaction is not going to happen. It's a wrong reaction. And if I were to measure the E0 cell, how do I measure the E0 cell for this reaction? Like, what's the potential difference?
So in this case, it won't be higher potential minus lower potential, right?
Yes, and I told you not to, I actually told you not to do that because I told you that the better method is reduction potential minus oxidation potential, right?
Negative 0.19.
So it's going to be negative 0.19 volts, right? Because remember, higher potential minus lower potential would always give you a positive potential, right? And it will also give you a positive potential for an unfeasible reaction, the one that you've written incorrectly, right? So reduction potential minus oxidation potential is going to give you the exact, like if it's unfeasible, it's going to tell you that it's unfeasible. Is that clear? So minus indicates that it's unfeasible. It's not going to happen. I mean, what this indicates, minus indicates, is that you got the arrow directions wrong. It's going to happen in the opposite direction. Is that clear?
Yes.
So now the task is, what will you do to make this reaction? How would you change the conditions so that this reaction becomes feasible? So if I want to make this positive, if I want to convert this into a positive potential, the same reaction, I want to make it feasible. So what should I do with this one? Should I increase it or decrease it?
Increase the concentration of SN2 plus.
Maybe the first thing, should I decrease this value or increase it?
Increase. Increase this value.
Will that make it positive? Like it can only, see, it can only become, I mean, this thing can only
decrease that value, decrease 0.15 and increase negative 0.04.
Is that clear? I mean, basically, who gains electrons? It's the higher potential that gains electrons. So this should be the higher potential, right? You should somehow increase this, right? And who loses electrons is the lower potential that loses electrons. So this should have been the lower value. So you need to decrease this somehow and you should increase this somehow. So you're going to try and decrease this, right? So what can you do for that? Like if you want to decrease it, what should you do? Like decrease it. Should it produce more electrons or less electrons?
It produce more electrons.
So you want it to go more in the backward direction, right?
Yes. So you
what do I do with 10-2 plus?
Increase the concentration of SN2 plus.
So we're going to increase it, or vice versa. We can do the other one. We can decrease 10-4 plus, right? Is that clear?
Yes.
And the other one, we need to increase that. So we're going to increase that, and how can we increase that? What should I do with? I can't do anything with Fe. What can I do with Fe3 plus?
So you need more of Fe. So you have to increase Fe3 plus.
Okay, so you should increase Fe3 plus. So coming back to this, where's the? I mean, make sure you have this. I mean, you get stuck over here. I mean, you get it right eventually, but make sure you get this right. That if you want to decrease the potential, if you want it to become more negative, you want the reaction to produce more electrons, right? So you're going to favor that reaction. So, and the other one is if you want to increase it, if you want to make it more positive, then you want the reaction to gain electrons. So you're going to favor that reaction that gains electrons. So you could remember this one, like if you want to make it more negative, it should produce more electrons. So it should favor that reaction that produces more electrons. So this is what you're going to do. An unfeasible reaction will turn into a feasible reaction. But you can't do that for all reactions, because even by changing concentration, you can only do just a slight, it will only become slightly higher or slightly lower. So if the potential difference is like, if the potential gap between the two reactions is huge, then you can't do anything about it. Is that clear?
So can you please repeat it?
Yeah, I'm just saying that if this had been 0.8 volts instead of 0.15, you would not have been able to make it into a feasible reaction, because I told you that I mean you can increase it, but it will only increase by a very tiny amount. Like it can go up till 0.1 moles, right? Do you get my point? And you can decrease it, but you can only decrease it by a very small amount. Like it could go down to, let's say, 0.02 volts, right? So by changing concentration, you can't really change the values a lot. It will only be a tiny change. But the tiny change would work over here. This would become the higher potential. This would become the lower potential. Is that point clear? Like if this turns into 0.05 and this turns into 0.02, then obviously this reaction becomes feasible, right? But the thing is, so if the potential gap, like if this had been a very high potential, this had been a very low potential, then you changing the concentration is not going to change the feasibility of the reaction. Is that clear? Is this clear?
Yes, sir.
Achha, so that's about so we're going to practice those in past paper questions. So before doing anything, let's try and do some questions. And I'll just do 1 second. So let me open. We're done with most of the stuff. It's electrolysis and where's 2020. So the first question in this one, that's kind of a difficult question, and we have done this, but not in this way. I mean, the first question is it's slightly tricky, right? So let's try and solve the first question. We've got they're saying that this is the overall reaction, right? So they're saying that this is the overall reaction. How do you get the overall reaction? It's the sum of two reactions, right? It's the sum of the oxidation reaction
The reduction.
and reduction reaction, right?
Yes.
So that's what we've been doing all the time. But in this question, the thing is they've actually turned it upside down. They've given us the overall reaction, They've given us the oxidation reaction, but the reduction reaction is missing. And they're asking us to deduce the half equation for the reduction reaction. So, I mean, do you get the question, right? So so what you have to, so how can you solve that? What you can do is, you've got this equation. You take out the oxidation equation from this. Whatever is left is the reduction equation. Is that clear?
CO2 will form 6
Then
C6H12O6. That's the reduction part.
no, but not that simple, because remember you did like, how did you make the equation? You also balance the number of electrons gained and lost before adding them up, right?
Oh, yes.
So the thing is slightly harder than that. Like, you've got this, now you want to go back, and they didn't tell us, like, is it getting multiplied by 3 or is it getting multiplied by 4? Do you get my point? Like, imagine one of the equation is missing, but they just gave us that 10 4 plus 2 electrons 10 2 plus, right? And they didn't tell us that is it getting multiplied by 3 or is it getting multiplied by 4. So the first thing would be to find out what would you multiply this with, and then you can add them up, right? So I need to find out what this should be multiplied with. One easy way to figure that out is, there's O2 over here, and there's O2 over here. Which is the substance, firstly, which is the substance that is getting oxidized? O is -2, right? O is -2 everywhere. And that O -2 on the left side is turning into oxygen, which is 0, right? Is that clear?
Yes.
So that is getting oxidized. So that means all this oxidation part is coming from this equation, right? So you got 6 O2s over here. So you should have how many O2s over here? 6 O2s, right? I mean, it's the same way over here. Like, if you see 3SN4 plus over here, and you're given this equation, so that equation must be multiplied by 3, right? Because the final thing has 3. So I'm going to kind of rewrite this equation. I'm going to rewrite this equation. So if I multiply this by 6, it's going to be 12 H2Os. And on the other side, there's going to be 6 O2s and 24 H plus 1, right? And 24 electrons, right? So that is my oxidation equation. Is this clear, this first step? I mean, the first thing is you're going to find out what is it getting multiplied. I mean, what is this equation getting multiplied with to give you the overall equation? Now we're going to come to the reduction equation. And I have no idea what the reduction equation is. And the two equations and the reactants must add up to give you the final equation, which is 6 CO2 plus 6 H2Os. So it's like adding things up. It's like, I mean, the first equation gets added with the second equation, you get this product, right? And the product is C6H12O6 plus 6O2, right? So that is what you're getting. Now, first thing, let's look at the left-hand side. 12 H2Os. What should I add over here to give you this? I mean, one thing is I should add what? 6 CO2s, right?
Yes.
So I should add 6 CO2s. But there are 12 H2Os over here, and there's 6 H2Os in the final equation. So 12 H2Os, I need to add -6 H2Os to it. Is this point clear, that one equation gets added with the second equation to give you this, right? Now, the only way that's possible is that 12 H2Os, you add -6 H2Os to it, then you're going to get 6 H2, and then you're going to add 6 CO2s as well. That's how you're going to get this, right? So is that clear, that you would have to subtract 6 H2Os from it? Clear?
Yes.
Same thing over here, 6 O2, so that's there. Where's the glucose coming from? It must be coming from this side, right? Is this clear? And then you see this 24H plus 1, but the final equation doesn't have 24H plus 1. That means
You have to subtract 24H plus.
and it's got 24 electrons being produced over here plus 24 electrons. You don't see any electrons over here.
Minus 24 electrons.
Right. So you found your reduction equation. Now the only thing you have to do is rearrange it. Like an equation never has, like a chemistry equation never has negative signs, right? But it's like a math equation. So that means this minus 6H2 is actually on the right side. Is that clear? I mean, if I rearrange this, so all the signs are positive. There's 6 CO2, 24H plus 1 and 24 electrons must be on the other side. That's reduction happening, plus 24H plus 1, plus 24 electrons. Is this clear?
Yes.
And on the other side, it's going to be glucose C6H12O6. And minus 6H2O, take it to the other side, that's going to be plus 6H2O. So that's going to be plus 6H2O. So you finally managed to actually make the final equation. So this is slightly tricky, like, and you can, I mean, this one was tricky. Even for these reactions, it's going to be kind of straightforward. But the problem would come when things get simplified. Like when you make, I think we did do simplification. I mean, we did do equations where things were getting simplified. Like for example, these chain reactions. Not the chain reactions, the chain reactions. Did we do any reaction where things would get cancelled out at the end? So anyways, I don't think there was any reaction that we did. But the thing is that sometimes what will happen is that you're going to have an oxidation reaction and a reduction reaction. And the final equation would be a lot simpler because things would kind of get cancelled out. We did one of them, the chain reaction. Like if you look at the chain reaction, although it was multiple reactions, but when you added them up, but at the end of the day, when you added things up, things kind of got cancelled out. Like this is the 10. We didn't actually perform the B. Did we do the B Fe3 plus reaction? I don't think. I mean, like even over here, when we did the whole chain reaction, the 10, I mean, the overall reaction at the end was 10. Things got cancelled out. Like if you have common things coming on both sides, they get cancelled out. Is that clear, Ranjali?
Yes.
So that is why the water molecules went missing. Like you had 12 H2Os and all of a sudden you had, in the final equation, you had 6 H2Os. The 24 H plus 1 went missing because things that appear on both sides would eventually get cancelled out. So the overall equation had a lot of things missing. So this is how you're going to do that. You're going to try and find the missing equation. The first thing was you're going to find the equation, the number that's going to be multiplied with the oxidation equation by looking at the overall equation. And then it's just math. This is the final equation. That's your oxidation equation. You find the missing values. And so 12 H2Os, you should get 6 H2Os. So that must be minus 6 H2Os. 12 H2Os, the final thing has 6 CO2. So there must be 6 CO2s being added to it. So is this clear, this part?
Yes.
And over here, they're asking you to draw a label diagram. So we're going to do these questions. The other ones are kind of the same. So we'll probably do that in the next class then, tomorrow then. Okay. So we'll finish the chapter. We're almost done with the chapter. It's just electrolysis and Faraday constant that's left. And otherwise, electrolysis is kind of the same, but we'll just quickly go over electrolysis. And Faraday constant is very easy. But we'll do some past paper questions as well. Let's continue tomorrow then.
Electrolysis?
Yes,
The
electrolysis is the same. Electrolysis is that you've got cathode and you've got anode. Cathode, the substance would gain electrons at cathode. Reduction would happen. And who gains electrons? The one that has the higher potential. And you've got a bunch of species at anode and they like to lose electrons. And who loses electrons? The one that has the lower potential, right? So we'll do electrolysis tomorrow. So let's continue tomorrow. Okay, Raji, take care.
so bye. Thank you.